Hello, my name is Gonzalo Abad, and in this tutorial we are going to do current loop dynamic analysis in a wind turbine based on double-fed induction generator. All the information related to this issue, to this topic, can be found on these books, all of them edited by Wiley. More specifically, if we go to this book, Chapter 10, we open the digital version, and if we go to page 282, we see how the current loops of the rotor side converter behave in a simplified way as a transfer function of second order. 1, 0, and 2 poles. This happens for D component of the current and Q component of the current. What I want to say is that all these current loops based on reference transformations from DQ to ABC and so on, the PLL and so on, which is quite complex thing, can be quite accurately modeled as transfer functions of second order. Sorry. If we go to the Simulink program, we will continue from the Simulink program as we left in previous tutorial. Let's open it. Here it is. I want to say that the rotor side control, this is the converter, this is the double-fed induction generator, and this is the control. These current loops, which is this part, together with this other part, can be simplifiedly represented and quite accurately as these transfer functions, and both for D and Q current loops are the same. In the same way, if we go to the grid side converter, which is this one, and to its control, and if we go, as I said before, to this book, more specifically to chapter 4, if I'm not wrong, yes, this is the page where we need to go. And again, we have an equivalent analysis in which the conclusion is the same. The grid side converter control, the current loops, can be simplified, D and Q current loops to transfer functions of second orders, 1, 0, and 2 poles. And at the Simulink program, this is the program, this is the grid side converter control, these are the loops together with this part. So if we analyze these two current loops in a more generic way, what I mean is, what we realize is that the rotor side converter behave as these transfer functions. Here we have an inductance of the open loop, and here we have the resistance of the open loop as well. And if we go to the grid side converter, we have something equivalent, transfer function which is totally equivalent. Here we have a different inductance of the, in this case is of the filter, grid side filter, and here it is the rotor, the resistance of the grid side filter. So if we do a more general approach, a more general analysis, we can say that those loops behave as this transfer function. In this case, I have put a general inductance and a general resistance. And this can be applied to many machines. these current loops can be in general simplified, or can be found the equivalence to the standard denominator of a second order system. Okay, so if we do the damping ratio equal to 1, which means that we have two real poles in the same location, we have this. And in this way, it is quite simple to choose the proportional and integral gains by means of these two quite simple formulas. So here we can choose omega n, which are the poles of the closed loop transfer functions, real poles, where we want to locate them according to the dynamic performance that we want to achieve, or whatever the requirement it is. And by these simple formulas, by simple equalizing of these denominators, we can achieve this. Then, if we apply unitary step response to these current loops, we have this one integral 1 over s. We need to include it here, so this is the input, 1 over s, which is a unitary step response. If we divide this transfer function into two factors, we have this. And if we apply inverse Laplace transform, we can obtain the temporal, the current, in function of the time. And here we have one term related to this transfer function, and another term, which is a little bit more complex, related to this transfer function. Finally, if we group some terms, we see this term and we see this term, which are quite simple, quite equal, quite equivalent. If we group, we obtain this term and this other term. This term will be 0 at the steady state, and this term will be also 0 at the steady state. Therefore, at the steady state, as we have chosen the integral gain equal to this value, and if we substitute this value into here, we realize that finally the current will be 1. So we see that how the dynamic behavior is given by omega n in these exponential terms. In general, this term is responsible of an overshoot at the dynamic response when we apply an unitary step, and depending how much is the difference between these two terms, how big is this amplitude, this overshoot could be bigger or smaller. And we can say that once we have analytically represented the current loops, we can apply any type of theory from the classical automatic control theory. So we could also cancel zeros and poles or whatever. This is just one example. This is just one way to do it. Okay, so if we go to the Simulink program and if we open the initialization program, here it is, we can use, let me open there and open here, we can use this initialization program in order to do the analysis that we want to do, and it is very useful. So for instance, if we go to the rotor current loops, we can rotor, the numerator, will be like this, this value, sorry, and the same for the integral gain, and both should be divided in this case by the, in this case, the inductance. This is the numerator, and the denominator can be, for instance, that will be, we can just say, for instance, yes, we can do it in this way. There are several ways to do it. Sorry, let's go back to here. The denominator will be 1, 2 multiplied by omega n of the current loop, where we have located the pole, and in this case again the square. These are for the, this is for the rotor, and for the grid state converter we could do exactly the same. Let me find where it is. Yes, it is here, so we can place it here. Obviously the proportional and integral gains are going to be different. Just add here G, and in this case the inductance that we are dealing with is the grid side filter inductance, like this, and for this we have put here as well G, and this is going to be the numerator of the grid state converter and the denominator of the grid state converter. We can initialize the program. Okay, nothing wrong has happened. So if we go to here, for instance, we can do the step response of the grid state converter, like here. Let's wait. It takes some time. So here it is, more or less. In 15 milliseconds, it reaches the steady state. This is the overshoot that we were speaking about, but basically is real pulse dynamic response. Then also, we can do the same, or a similar analysis with a body diagram. Let's see, here it is. Here we have the bandwidth, more or less, until somewhere there. This is in radians per second. So this is the closed loop behavior of this current loop of the rotor side. If we do the same, for instance, let's do the hold on. If we do the same, sorry, that was the grid side converter. If we do the same for the rotor side converter, which is here, let's do the same for this grid side converter. Let's find, sorry, this one from grid side converter, and let's do the same for rotor side converter. We see that this new one, the rotor side converter, has been tuned with a bandwidth much more wider. We don't really need it, so let's approximate it to the grid state converter dynamic or bandwidth, like here. Let's save and then see what happens. We don't need one. Okay, let's eliminate this one. Super, it's not working. Let's try again. Okay, doesn't matter. Let's do again the body plot. And here it is, the new one, which is in this case the blue one. We have both current loops of the grid state converter and of the rotor state converter with a bandwidth very similar. Anyway, we can do any analysis, any theoretical analysis that we can do thanks to this theoretical approach. Okay, once we have this, let's go to the Simulink program and let's compare, or let's validate if this simplification, if this approach of second order system is good or not in our actual or real simulation program. So, first of all, if you remember, we will perform in symmetrical voltage dips, and in this case we are not going to use the symmetrical voltage dip. Therefore, we will use normal grid voltage. We don't really need so big simulation, so long simulation, sorry. So let's put it there. And then, yes, let's wait. Let's start from here. For instance, we need this behavior, and therefore we need a from to. Let's take it from there and let's put it here, for example. So this will be the entrance, the input, copy, paste, okay. This is one, and the same for Q. Okay. Then we need the second order system. We need a transfer function. So let's go to the Simulink library. Let's go there. This is only for visualization programs, so we can do it in the continuous domain, in Laplace domain. We don't really need to discretize it. Let's eliminate the name, as always. This is going to be, let me remember where it was. Okay, and like this we call it. So this is going to be the numerator, and this is going to be the denominator, therefore like this. Okay, we can make it smaller, and therefore what we obtain is just the theoretical actual IDR. So let's call in a different way, for instance like this, from model. And the same we do for the Q. Let's group it. Loops validation. Let's call them like this, and this is just for visualization. Okay, so we can go to the monitoring program and let's compare them. Let's do bigger. Let's add a third input here. Let's make it smaller. let's do this, something bigger. Let's copy there, and this is going to be the other model approach, the theoretical model approach, simplified, and let's compare if it is good approach or not. This is IQ. I'm trying to find ID. Yes, here it is. This is the third input. Again, let's do it, sorry, smaller, something smaller, not so much, sorry, like there, and like there. Let's copy, paste, and this is going to be the model. This says that I have forgotten to call this IQ. Yes. So that's it for the rotor side converter control, and we could do the same for the grid side converter control. Let's put it there. So here we need as inputs ID G, there it is, okay, and this will be IQ G, okay, and this will be model D component, sorry, this is G, and model Q component, IQ G. Okay, IDG and IQG. And if we go to the monitoring block, again, we go to this grid side converter control, we could do just exactly the same and compare the actual or the real, values. Let's copy there. That will be model okay, and here as well we can do the same. 3, sorry, let's do it smaller, and this will be the model approach. Okay, so we can save. So we simulate in order to compare whether the model approach and the real or Simulink program approach are equivalent or the same. Let's perform ID references at, for instance, 2.5 seconds, and not so big, because we could go to saturation. Let's perform this current step input at second 2.5, and let's do the same for the QG. So therefore we don't need this, and neither we need this. I don't know how much could we say at the same time. I don't know, 150 kilobars, for instance. Yes. Positive or negative, it doesn't really matter. So in general, we don't really use this type of step demands, but in this case, in order to validate this approach in a very demanding input demand, sorry, so let's do it in this way. So save, we just initialize again, just in case, okay, and we simulate. We are using the accelerator, so we will need to wait some few seconds. Okay, so it seems running already. We don't need this. Let's open the windows that we need. Okay, and let's wait. Just keep in mind, as always, that the startup is not made in a very realistic approach. So let's wait and forget about the starting process. Just keep in mind that here at the scopes, in the rotor side converter, and here and here, and in grid side converter, we have add some new entrances, the orange ones, here, 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 and there. So time is running, and the green side converter is almost controlling the DC boost voltage with some oscillations. We could prepare better parameter gains of the DC boost voltage, but anyway, let's leave them there. And here also the rotor side converter seems to be working properly at 2.5. Just keep in mind that we are going to perform here and here step demands. Right now has happened. Let's wait until the end of the simulation. And that's it. Okay, so let's have a look about the current performances that we have. Let's wait. Here it is. So more or less in there. So from here to here, and let's do the zoom of the Y-axis. Here it is. And the other current loops, the Q component has not seen or noticed the difference. Therefore, neither the torque. Here are the voltages, how do need to react. And as we have predicted in the theory, we see how the theoretical model, which is the orange, goes quite well with the actual simulating program, which is the blue one. And if we do the same at the grid side converter, let's analyze it. Let's do something similar at 2.5 seconds, more or less there. There we have performed the step. Like 2.45 and 55. Let's do very similar zoom. So here again we see how the theoretical approach, the orange one, goes quite well with the blue one, which is the actual one. Obviously the blue one has switching frequency, ripple due to the switching frequency that the model, the simplified model, doesn't take into account. Here we have the references. If we want to go further, we need to realize and we need to take into account a very important issue that happens in reality, and we often we don't really model it. In general, hardware implementations, there is one delay between the control and the PWM, or the modulation implementation. If we go again to the presentation, here I have another slide trying to explain it. Sorry, let's finish with this. Yes, as it is very well explained in this book, which is a very good book. I have learned a lot thanks to this book. As I said before, here it is the modulation triangular, and here we have the voltage references, the sinusoidal voltage references, that they are changing over the time. So here we normally have the sampling, the measurement of the currents and the speed. Then the algorithm needs some time to do its calculations, and once it finishes its calculations, the PWM output is performed just one sample period later in the next triangular. So here we measure, then we do the algorithm with these measurements, and we perform, or we perform the outputs just one sample period later. This is one delay, as I said before, that should be taken into consideration here. What means that if we go to the books, for instance here, what means this is the part of the model and this is the part of the control, and here we have the delay. This means these delays provokes that these two cancellations are not made properly of the coupling terms, and therefore this will not be 100% accurate. So in order to tackle with this problem, as recommended in this book, what we could do is just at the voltage reference, in order to compensate or just this delay, we put in advance just 1.5 omega and sample time. Okay, so we advance up to this point. We measure here and we compensate the delay by phase lagging the voltage reference to this value. Okay, so let's model this phenomena, and therefore what we need here in both converters, again, we need the discrete, we need to perform this delay, for instance with this simple block. Let's remove, as always, the block name, and let's use as delay the switching period of the power electronic converter. Yes, okay. So we add it there. This is one part for the rotor side converter, and we do the same for the grid side converter. So with these two elements at both converters, we are modeling this delay, and in order to compensate it, let's do this thing in both converters. So here, this is very simple to do. Just at the theta angle, we need to add, well, simple, maybe not so simple, but let's have a look. we need to add one angle to this theta angle, sorry, just is there. So here we need omega r, because that's the frequency in which this voltage vector is rotating, omega r. So for instance, I think, yes, we have here omega r, so we need to go to, like for instance there, and that will be omega r. This is omega r, so therefore we need this, and we need to probably from here we can take one, that will be omega r. Let's do some space, and this is the angle that we are going to add, 1.5 multiplied by the input omega r and multiplied by 1 over the sample period. So this is just this value. And we can do the same for the grid side converter, which is here. This is the angle theta. Okay, so in this case we should do the same, but as here we have this feed-forward term, things are not going to be so simple. Let's have a look. Yes, we should compensate at this stage. Let's do some space. Okay, so this is ABC already, therefore we need to pass to alpha beta again, then we need to perform, let's make some space, the angle compensation, that should be like this, with a angle theta that we are going to place it there, and then once again we need to go from ABC to alpha beta. This is not so simple, quite many transformations, but anyway. Yes, ABC output, and this is the angle theta. Okay, so we can group. This is the group. Let's make some more space. There, there, and there. This is one term. Let's connect it there. Compensation, let's call like this to this program, and the angle that we need to compensate is just one constant, and this is going to be as before 1.5. In this case the grid side frequency is constant, therefore we don't need to calculate the frequency in radians per second, and then 1 over fs, sorry, like this. Sorry, there is one error. This is the frequency, and that's it. and this is the angle that we are going to compensate due to the delay. So we don't really need this block. Okay, so from ABC we again do alpha beta. We do the phase shift, and then again from alpha beta to ABC. I hope it works. This one was, this is one, and this is the other one. Okay, so let's save and let's simulate again the program. We don't really need, to simulate so much time. Let's simulate again with the accelerator. We will need to compile again, so let's wait. Okay, so it seems it's simulating again. Current loops at the grid state converter working, and at the rotor state converter we don't have speed enough yet, so we need to just wait. And just remember that at 2.5 we have performed the step inputs for both converters at the grid current, and at the rotor side current dereference. We don't do nothing here, here basically because it is commanded by the MPPT, but we could do it, and the same or something equivalent we do for this reference. We only do voltage reference variation in here. Let's wait. In this case, as we are switching at if I'm not wrong, we were switching at 4 kilohertz. This delay that we have at between the control and the modulator is not so big, so we won't notice it very much, but just in case when we need to switch, when we need to commutate at a lower switching frequency, this is what we should do in order to be more accurate with the theoretical dynamic response that we have predicted. So the step has been made and the new steady state has been reached. So the simulation is stopped. And let's have a look. Let's do the same as before. Here, for example, okay, and let's do the zoom. As before, more or less up to there. Even more. So we see that the thing has been a little bit degraded, but thanks to the compensation, the theoretical model fits quite well with the blue one, with the actual one. And if we do the same with the grid state converter, let's go up to there and let's do the zoom. There. Here it is the performance. With the with this delay that we are performing, that we are modeling and simulating, and here it is the performance of both loops. If we wouldn't use the compensation of this delay, probably this theoretical, the orange one, and the blue one will be farther away for both grid rotor side converter and grid side converter. Here we have the ABC currents. And here we have the DC push voltage. We didn't reach the steady state, therefore it is still oscillating. But anyway, we wanted to focus on this behavior. And we see how for this component we have very accurate, and for this component, for the Q component also, we have very accurate. Just keep in mind that we don't have to reach to the saturation, to the voltage references, because if we reach the saturation, obviously we won't follow exactly the dynamic that we want. Okay, so that was all. I hope it was useful for you, and thank you for your attention.